We saw in the lesson on electromagnetic waves that if an alternating current is passed into a conductor, an electromagnetic wave is produced. We also saw in the lesson on wave modulation that if a second, less powerful current is also passed into that same conductor, then intelligence can be passed with the electromagnetic wave. This is the fundamental basis of radio communication. An important part of this process is the antenna, or aerial, which is the conductor. One antenna is needed for transmitting the message, and one is needed for receiving the message. Before reaching the transmitting antenna, the message, perhaps a voice, is converted into an electrical message. This modulating signal is mixed with the carrier wave and then transmitted by the antenna. After reaching the receiving aerial, the signal has to be amplified, because only a fraction of the original current will be received, the remainder being lost in the ether. The amplified signal is then demodulated, in our example to speech, which is conveyed through a speaker. The size, the shape, and the material of the antenna are all important. The metal used must be a good conductor, such as copper or aluminium, and must not impede the flow of the electric current too much. Similarly, any cable used has to have similar impedance to the antenna, otherwise a resistance will be created where they meet and current will be lost. The size is particularly important. Ideally, it should be half the size of the wavelength of the radio wave. However, a quarter of the wavelength is nearly as good and has the advantage of being smaller. As a result, medium wave, long wave, and very long wave transmitters have huge aerial complexes, whereas VHF and other short wavelength antenna can be very small, such as in your mobile phone. Transmission in VHF with a wavelength of between 1 and 10 meters is therefore desirable, not least because of transmitter aerial size, which would range from half a meter to 5 meters. Here is a typical VHF aviation transmitter aerial, called a half-wave dipole or Hertz antenna. The formula for calculating the length in feet of a quarter dipole antenna is 95% of a quarter of the wavelength. So, if the frequency is 125 MHz, which is a typical VHF communications frequency, what is the ideal aerial length? Don't click to continue until you've got an answer. You should have been able to work out from the previous lessons that 125 MHz gives a wavelength of 2.4 meters. So, 95% of a quarter of 2.4 gives us an ideal aerial length of 0.57 of a meter, or 57 centimeters. Let's look at a half-wave dipole. It is divided into two equal lengths, with each half connected at the center to a feeder cable, which carries the alternating current. You will be familiar in your home with a ribbon antenna attached to your tuner. This is a half-wave dipole. The emission from a half-wave dipole antenna is greatest at right angles to the center of the antenna and at zero at the ends of the antenna. The pattern or polar diagram of the emission is called toroidal. It looks like a fat donut with the antenna in the center. Some half-wave dipoles, known as folded dipoles, have a second conductor joined to the ends. These are used to achieve a broader band of frequency emission, such as the aviation band from 118 to 136 MHz, rather than targeting a specific wavelength. The other type of communication antenna we'll look at here is the quarter wave or Marconi antenna. By placing a quarter-length antenna on, but isolated from, a metal surface, such as an aircraft skin, the metal surface acts as a reflector, and so the antenna size only needs to be a quarter of the wavelength. Because electromagnetic waves travel at different speeds through different media, for example, through metal, they travel at 95% of their theoretical maximum speed, the antenna length, when fixed on metal, must also be reduced to 95% of its maximum theoretical length. Aircraft have to communicate over the whole range of aviation frequencies, but they cannot use an antenna with varying length to match the varying frequency. So an electronic device is fitted in the circuit between the radio equipment and the antenna. This aerial loading unit samples the signal, then balances it for maximum antenna efficiency. Radio waves would normally travel in all directions from an antenna, but this would be wasteful for many systems, such as radar and instrument landing systems, which need to be direction-specific. The simplest way to achieve directivity is to add elements, called parasitic elements, to the antenna. If we place a metal plate 5% longer than the antenna at a distance of a quarter of a wavelength from the antenna, and in the same plane, it will act as a reflector. This reflector re-radiates the energy 180 degrees out of phase, with little signal behind the reflector and increased signal in front of the antenna. The signal shape is shown here. This process can be taken further by the addition of other elements in front of the antenna, also spaced at quarter wavelength. These elements are known as directors and are smaller than the antenna. They focus the signal out of or into the antenna, giving a stronger signal than that which would be generated by a simple dipole. These antennae are called Yagi antennae, and they are commonly used for televisions. However, directing a signal in this way produces side lobes, which transmit and receive unwanted signals, such as reflections from buildings. An application of the directed signal is the ILS. A narrow signal is produced from the localizer signal from an array of 16 or 24 antennae placed in line, with half-wavelength spacing, each antenna enhancing the signal of the other. However, side lobes are produced. Given that ILS systems transmit between 108.1 and 111.95 MHz, if we take a signal at 108.1 MHz, we can calculate the wavelength as 300 divided by 108.1, which gives 2.78 meters. So, the antennae should be spaced at 1.39 meters. The system produces two overlapping signals, which are modulated, one at 90 and the other at 150 Hz. The strength of the signal from each lobe becomes more noticeable as the aircraft wanders to the side of the center approach line. We will look at this topic in greater detail in the ILS chapter. Finally, in the context of directivity, let us consider the loop antenna. If a loop is aligned with a signal which is exactly at right angles, then the signal will strike both sides of the loop at the same time, and there will be no measurable electrical difference. If the signal is not at right angles, then the signal will strike one side of the antenna before the other. That is, the signal will strike the antenna at different phases, and the electrical difference can be measured, showing that the signal has come from the left or the right. Radar beams are directional, and they are narrow. Many ground radars produce an all-round picture, but this is because the beam is rotated. Radar beams operate at ultra-high frequencies, 300 to 3000 MHz, or super-high frequencies, 3 to 30 GHz. Because of the power required for these systems, waveguides are used rather than cables to carry the energy to and from the antenna. These are tubes or boxes, half wavelength in width, along which the energy zigzags. The waveguides may contain air which may be pressurized, or they may contain a vacuum. The most common type of radar antenna is the parabolic dish or parabolic cylinder. The shape of the dish is carefully constructed so that any point on it is equidistant from a point away from the dish, called the focal point. If the current is emitted at this focal point, all the waves to the parabola are reflected as parallel waves. Also, the path lengths FXA, FYB, etc. are all equal. Thus, the reflected wave is made up of parallel waves, which are all in phase, thereby producing a narrow beam of radio waves. Because the focal point is minute, the energy from the waveguide will cover a slightly larger area, and there will be some spillage of energy which causes side lobes to be transmitted. These may cause radar returns from outside the target area of the main beam. A much smaller type of radar antenna is the flat plate or slotted planar array. We have seen with the ILS localizer antenna that if a series of antennae are spaced at half a wavelength and are fed in phase, the energy from the antennae is enhanced. This is the principle of the slotted array antenna, and the energy is emitted from the multiple slots in the plate. This type has the advantage that the side lobes are smaller, thereby wasting less power. The RF energy is therefore concentrated into a narrower beam. It therefore needs less electrical power. This makes it a popular choice for airborne weather radars. Let's summarize this lesson. The size, the shape, and the material of the antenna are all important. Antennae should be 95% of half or a quarter the length of the wavelength being transmitted or received. Half-wave dipoles are divided into two equal lengths, with each half connected at the center to a feeder cable, which carries the alternating current. Some half-wave dipoles, known as folded dipoles, have a second conductor joined to the ends. By placing a Marconi-type antenna on, but isolated from, a metal surface, such as an aircraft skin, the metal surface acts as a reflector, and so the antenna size only needs to be a quarter of the wavelength. An aerial loading unit balances the dipole for maximum antenna efficiency. Directionality is achieved in the dipole by adding reflectors and directors. But it can also be achieved by receiving signals in two vertical elements, which will only be in phase when the loop is at right angles to the signal direction. The most common type of radar antenna is the parabolic dish or parabolic cylinder. These suffer from side lobes. A much smaller type of radar antenna is the flat plate or slotted planar array. The side lobes are smaller and need less electrical power. This makes it a popular choice for airborne weather radars. This concludes the lesson on antennae. The next one looks at the Doppler principle.